Hey guys, BuildZoid here, and today we're going to be taking a look at the Asrock X370 Taichi board. So, interesting little fact about this board, it shares its PCB with the professional gaming board, and actually shares its VRM design with the professional gaming. So the V-Core, SOC, and memory VRM are all the same. I do believe all the other minor VRMs scattered around the board are too. I'll only be talking about SOC memory and V-Core here because there's like all the other ones, there's so many of them and they don't really affect overclocking, so I don't feel they're worth covering. So the biggest difference for me, at least, between this and the professional gaming is the lack of the buttons here. I've tried to see if it's not possible to revive those, and it looks like they've removed a lot more than just the buttons themselves. Like, some of the actual wiring for them is missing, so that's a bit unfortunate. So you do actually have to use the front panel header here. It still has the post code at least, which is really useful. There's no dual BIOS on the board, which is another thing that I find rather annoying, but hey, you know, whatever. So yeah, with that out of the way, let's just get right onto the VRMs. So the main VRM block is this right here. And this is actually not a single, this is not one set of, like, this is not one giant 16-phase VRM. It's actually split right here. And I'm not actually, wait, I did the highlight wrong. Bleh. Need to avoid the capacitors because I'm not sure how the capacitors are actually separated between the VRMs, but there we go. That's better. So it's split right here, and this all is V-Core. So that powers your CPU cores, and then this right here, these four phases are SOC. So those are for the system system on a chip part of Ryzen. And in the future, I expect this to also power the iGPUs of AM4 APUs, but for now this only powers things like the PCIe controller, memory controller, USB, and some of the SATA stuff, because Ryzen integrates a lot of the chipset functionalities onto the CPU die, and that's what this VRM powers, all of that extra integrated functionality. So yeah, that was covered. Let's take so that's your two main VRMs. Now let's talk about how they're actually controlled and how much power they can deliver. So they're both controlled by an IR3, well, this chip right here, which is a IR35201. This is an 8+0, 7+1, or 6+2 phase voltage controller. Depends on what the manufacturer wants to set it to. Here on this motherboard, it's running in 6+2 phase mode. And it is doubled up, as we can clearly see. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, as well as 1, 2, 3, 4. So we have a 12-phase V-Core and a 4-phase SOC VRM, which means this right here, this 6+2, is actually running into doubling. And it is doubled using IR 3598s. These can function either as dual drivers or driver doublers. Well, basically, one IR3598 can run two phases, and it can either take in two PWM signals or it can take in one PWM signal. If there's one PWM signal going to it, it's running in doubler mode. If there's two PWM signals going to it, it basically acts as two individual driver chips just put into one chip, which saves board space and lowers costs of manufacturing for the board makers. So, you know, that's all very well and good. As far as control schemes go, the IR35201 is basically used on all the X3 high-end AM4 motherboards. Also, most of them are running it in the 6+2 phase mode, so this is really, like, there's nothing wrong with this. It's comparable to basically all the other boards. Some of the other boards are opting for 4+2, but generally on the high end, you're looking at 6+2 with doubling. If you go lower, if you go for more mid-range boards, you're looking at like 4+3. Without any doubling actually included, so you just get straight 4+3s. So yeah, there's nothing wrong with how the VRM is controlled here, and basically how to think of a short version of how doubling works is basically it's better than a 6-phase. It's not as good as if you had a real 12-phase, and it's arguable if it's better than than a true 8, right? Like a doubled up 6 is a doubled up 6 producing 12. Like it depends on the application. If a 8-phase true might not actually be better, but we don't actually have any true 8-phase AM4 motherboards, so here this is really the best you can get for. Who the hell is messaging me? Why don't I mute everything? There we go. Let's just keep rolling. So yeah, so control scheme is fine. Let's move on to how much power the MOSFETs can do. And for actual power delivery, we have these blocks right here. And these are Texas Instruments, so TI CSD 8 7 3 5 zeros. Keep mixing up the position of the 3 and the 7 and also that 8. But yeah, so these are CSD 87350s. And these are dual NFETs. Texas Instruments calls them a half-bridge power block, but really it's just 2 MOSFETs on a single chip, and we've seen that a ton of times before. So dual NFETs works just fine. These are rated to do 40 amps at 125 degrees centigrade, 500 kilohertz switching frequency. Right, running out of space here, and 1.3 volts output voltage. The voltage is a little bit low for a Ryzen system, as typically you'll be running at around 1.4 volts for overclocking. That's the general maximum. If you're really, really pushing the CPU, then you might go up to 1.5 volts for benchmarks and such. But yeah, 1.3 volts is fine. With 12 phases here, that does mean that this VRM is capable of outputting a maximum of 480 amps. However, that assumes you can actually keep it at 125 degrees, and it'll put out 105 watts of heat. Or slightly less. The data sheet isn't super clear on which of their heat output graphs is the better one to go for, so I just went with the worst case scenario, which looks at 105 watts heat output. Now, the great news for you is Ryzen doesn't actually pull anywhere near that much power. It's really, really power efficient. From my own testing, my Ryzen 7 1700 at 3.95 gigahertz and 1.45 volts only pulls about 100 amps from the V-Core VRM, as far as I can tell. Now, the software claims it's putting out 144 amps. Except if I was to believe the software, then my Ryzen CPU is somehow managing to burn 211 watts, while there's only 170 watts going into the 8-pin power connector here. And I went ahead and checked, and this 8-pin power connector provides all the power for the V-Core VRM, all the power for the SoC, and the RAM. So there is absolutely no way the CPU power draw readings or current draw readings were actually accurate, because they don't line up at all with how much power was going down through the 12-volt connector right here. And this is the only thing powering the memory V-Core and SoC VRMs. I went and checked that with a multimeter, because initially I was like, oh, there's no way the software is this wrong. But it is. It's off by 40+% on current readings, so it's just completely garbage. But yeah, Ryzen should pull at 4 gigahertz, 1.4 volts. You're going to be looking at around a maximum of 100 amps. And at 100 amps, this VRM right here will put out about 12 watts of heat. So not much, which is actually, that's really great news. The heat sink, like, you don't need a heat sink on this VRM for daily overclocking. And I know the board comes with a heat sink, but it's not really, like, you don't need it at all. Even if you push the VR, if for some reason you manage to get a Ryzen CPU to pull 240 amps, then you're looking at about 35 watts heat output, which then the heatsink that's on the VRM actually starts being useful, and you might want to also get some airflow over that. But again, Ryzen pulling 240 amps, that's going to be, you'd need like 1.8 volts or something to do that. Well, no, way more. you'd need... I don't think it's actually possible to get Ryzen to pull that much power without, like, the CPU actually failing before it hits that kind of power consumption level. So basically, you know, you're never going to get near that maximum 480 amp power consumption. You're not even really going to reach half this VRM's current capability. And at 100 amps current draw, which is sort of realistic usage scenario, this VRM is perfectly fine. And that's 100 amps on the 8-core Ryzen. So this VRM right here is like, this is one of the main reasons why this motherboard hasn't gone through the window. Because it is really, really nice physically. Like, the VRM, the MOSFET selection is awesome. It's incredible. It's really, really nice. It's by far one of the... Actually, it is... I think it might actually be the straight-up best VRM currently available on the AM4 platform. It is, actually. So, it is 100%. Because the Gigabyte is a 6-phase... different components, but I'm not going to reveal how much. Gigabyte's a 6-phase, can't do as much power. The Crosshair 6 is an 8-phase, same components, but it's an 8-phase, can't do as much power. And then there's the X-Power from MSI, which is just, well, I've done a PCB breakdown for the X-Power. It will be going up on the Gamers Nexus channel sometime soon. And, well, let's just put it this way. Prepare to be extremely disappointed by a motherboard that expensive. So this is by far the best V-Core VRM you can get on an AM4 motherboard. You know, and that's great. Main reason why I haven't thrown the board away yet, or returned it to Asrock. So now if they just get their BIOS to work properly, you know, this could be a really, really great board. Now then, moving on to the SOC VRM, same... Texas Instrument CSD 87350s, and except here we have 4 phases, so maximum current throughput is 160 amps with 35 watts of heat output at that power throughput. And interestingly enough, that's the, yeah, you can see how more phases gives you more power, because this is 240 amps, 35 watts. This is 160 amps, 35 watts, because this is just a 4-phase, but so 160 amps, 35 watts. However, realistic usage scenario, at least right now until we start seeing APUs. I'm certain that once we start seeing AM4 APUs, the SOC will get, like, more important in terms of power throughput. But as of right now, on my Ryzen 7 CPU, the SOC seems to only supply, like, the SOC VRM needs to only do about 20 to 30 amps. And that's at 1.2 volts, and so, you know, realistic operating scenario, this VRM right here will only be putting out about 4 watts of heat, which is great news, because that's nothing. So this right here also doesn't need a heatsink for the SOC VRM. So if you're just doing daily overclocking, this board is just, like, ridiculous overkill. Even for extreme overclocking, it's still pretty ridiculous overkill, especially considering that liquid nitrogen will actually help cool down the area around the CPU socket, because Ryzen is a no cold bug CPU, so you will actually get, well, the cold will go into the CPU and then through the pins and then through the copper actually connecting the V-Core and the SOC VRMs to the CPU. So this VRM is just total overkill, and there's nothing to complain about here. Now then, let's move on to the memory VRM located up here. It is controlled by a UP 1674, and that's a 2-phase voltage controller, and I was too lazy to look up the data sheet for how far it can actually go frequency-wise. Either way, this is like, you can look it up yourselves. This is actually, like, interestingly enough, the Taichi is one of the few motherboards with 2-phase memory power, which I think is actually extremely overkill, and I really, like, this is where Asrock starts going, I think, a little too far, because these MOSFETs are, again, these. They're using these TI CSD 873050s, 40 amp dual NFETs, again, for the memory VRM right here. And that's just dumb, because DDR4 doesn't pull anywhere near that much power. I mean, it's not dumb. It's nice to have overkill, but the problem is, I'd rather lose the 2 phases Like, I'd rather not have an entire phase and use a cheaper MOSFET and then get my these two buttons back than this. So, yeah, you know, I would have happily traded some memory VRM capabilities for, you know, power and reset buttons, but it's really a more me-centric complaint than anything else. But yeah, basically the end result is this VRM can do a maximum of 80 amps at 18 watts of heat output. Again, assuming 125 degrees, 500 kilohertz switching frequency, 1.3 volts. Now, for DDR4, you're looking more to, like, DDR4 maximum safe voltage, you're looking at, like, 1.45 volts. This board actually limits you to not go over 1.8 volts. That's the absolute maximum on the memory VRM, at least while I had it in manual mode. So I'll have to check if it can't go higher by any chance. But for right now, I think the limit is 1.8 volts. And you still don't want to run that daily. For daily, you're looking at 1.45. DDR4 really doesn't pull a lot of power. And considering that this VRM is also hooked up to that same 8-pin here, you know, I don't have good data for how much DDR4 actually pulls, but I'm going to say that 10 amps is a high estimate because that works out to about 15 watts with 10 amps, 1.45 volts. And that's, you know, like heat produced by the actual memory sticks. That's a bit high. And that's assuming you have 4 memory sticks and you're actually running them at like high voltage and high clock. And so again, this is just extremely overkill because even if you're pushing 10 amps through this VRM, which I still think is way too much, it's only going to put out 2 watts of heat. So this thing right here doesn't actually have a heatsink, and it doesn't even need it. Because, again, it's total overkill for DDR4 power. So, yeah, Asrock have really gone and just splurged all over this motherboard in terms of just MOSFET selection. Because they basically went and took one of the nicest MOSFETs for motherboard usage. Like this, you find this part on a lot of really high-end motherboards. We're talking like ROG boards from Asus, and a lot of the top-of-the-line boards from Asrock just use these. And, well, they're everywhere. They've literally shoved them everywhere. So, you know, it's nice, but I'd rather have a cheaper memory VRM and have my buttons back. Thank you very much. Also, the BIOS would be nice if it worked. You know, that'd be great if they could fix the BIOS, because right now it's just, yeah. But, you know, that'll get solved in the future. Physically, the board is absolutely amazing. Best V-Core VRM for AM4 right now. SOC VRM is not the best. The SOC VRM is like on par with all of the other high-end boards, because all the other high-end boards are also 4 phases and similar power capability components. Except the X-Power. The X-Power is a lot less efficient, but, you know, the SoC doesn't really do anything right now. And the memory VRM is massive overkill. That's actually, like, the biggest difference between this board and a lot of the other boards. This memory VRM is 2 phases. Most of the AM4 boards are 1 phase, with some of the high-end boards being 2 phase. And this one's also using really expensive MOSFETs, whereas ROG, actually, the Crosshair 6 Hero, I've done a breakdown of that board for Gamers Nexus, and they use they use adequately sized MOSFETs for a memory VRM, as in they're pretty garbage, but it's a DDR4 memory, it's a DDR4 VRM. You don't need incredible MOSFETs on that. And then, well, the X-Power actually has a comparable in terms of power throughput, but a lot less efficient memory VRM, though, again, at 10 amps, it doesn't really make that much difference between the boards. So, yeah, you know, it's a nice board. Physically, the BIOS really needs some work, though, and that's it, you know. I think if you don't plan to use the BCLK overclocking, this board is really great, like overkill wise, for the VRMs. And I really think, actually, if you don't need the BCLK feature, you can go buy a cheaper board, because Ryzen, like, from my testing, it doesn't pull any power. It's really, really low power compared to, like, say, AM3, For example, AM3 CPUs would easily pull 140 amps plus from the V-Core VRM. And that's when we were having like, oh, this motherboard has a very high probability of exploding if you overclock an 8-core on it. But Ryzen doesn't need a lot of juice. So this is really, really overkill. And so are a lot of the other top-of-the-line boards. So really the main reason I'd get this is if you need the BCLK overclocking, which currently doesn't work that great. So, yeah, that's about it. Actually, no. One last thing I wanted to mention. This V-Core VRM. Almost forgot about that. It is in my notes. I just forgot to check them. This V-Core VRM has LLC settings in the BIOS. And Asrock's LLC settings, you have level 1, level 2, 3, 4, 5, right? So you have 5 levels of LLC. And so I set 1.375 volts in the BIOS, right? This is the voltage I set. I do believe it was 4 gigahertz. No, it might have been 3.9. No, it was 3.7 gigahertz because I didn't know where the voltage would actually end up. So I did some LLC testing, and at idle and at load, you had these voltage differences on. So I was actually measuring. Oh crap. Well, this capacitor right here, I was measuring my core voltage off of that, which is a little bit far from the CPU socket, but right now I don't have a great way to stab a capacitor closer to the CPU. Either way, the results I got was 1.375 volts set in the BIOS with level 1 LLC. It idled at 1.381 and ran Cinebench at 1.461 volts. That's a lot of overvoltage. Now, the software actually reports very different voltage levels, completely different voltage levels, but the software also reports Ryzen pulling 140 amps, which I know isn't physically possible because there's not enough power going into the VRM for that much power to come out of the VRM. So, you know, I'm having a really, like, the software reported that this was pretty much flat. I have a really hard time believing the software when it can't even read power consumption properly. So I don't trust the software voltage readings at all. Physically, I was getting this. Level 2 was 1.380 volts. With load going to 1.445 volts. Level 3 was 1.380 and 1.43? Yeah, 431 volts. That load being Cinebench 11. 11.5. And level 4 was 1.377 idle and 1.401 load. And then level 5 was 1.375. So we actually got the voltage I set at idle. And then under load, it was running 1.385 volts. So basically, I've decided that all of my overclocking I'm doing on this motherboard, I'm doing it at level 5 LLC instead of level 1 LLC, because that is a lot of voltage. Like, if I were to trust that the LLC was actually keeping the voltage flat, that would mean that the resistance between the V-Core VRM right here and the CPU, well, wherever the actual sensor for the V-Core VRM is, the resistance between the capacitor I was measuring on and that sensor would have to be like 0.6 milliohms, which is pretty high, because you can actually get MOSFETs that have a lower switch RDS on than that, and those aren't even copper. So I have a pretty hard time believing that there's that much voltage drop between the core like the VRM and the CPU. And so I just run level 5 LLC on this board because level 1 is a lot of overvoltage. It's just like this I would just straight up consider unusable, this right here. And this right here, I mean, this I would say is kind of okay, but basically from level 3 to level 1, it's just really lots and lots of extra voltage. And yeah, you know, it's just no. If you're overclocking, you want a flat voltage. You want a really, really flat voltage, and this board isn't doing that at level 1. At least not with for my measuring equipment. In software, it says it's flat, but the software also says, you know, garbage about power consumption. So, don't really like that. I need to do some more. Like, I need to figure out some way to investigate this. The problem is, it's, well, basically, let's say you set 1.4 volts, right, and then you run level 1 LLC, then you're going to be getting like 1.48 or 1.49 volts under load, and that's a lot of, you know, 1.4 would transform into that under load, and that's well above the, like, motherboard manufacturers recommend 1.4 volts maximum. AMD recommends only 1.35 volts maximum. And then if you run level 1 LLC, then you get like almost 100 millivolts more than what almost 100 millivolts more than what Mobo makers recommend, and over 150 millivolts more over what AMD recommends. So it's not safe for long-term usage as far as I'm concerned, as it could cause your CPU to degrade. The other issue is it'll just, like, it skews your testing results as far as I'm concerned really badly. So I recommend just using level 4 and level 5 LLC, because this board otherwise boosts a ton of voltage for no reason. So yeah, that's finally it for this video. The board's nice. The LLC is a little insane. You know, physically it's great. Thanks for watching. If you liked this video, there's a like button you can click. That lets me know. If there was any issue you had with this video, there's a dislike button. You could click that as well. To let me know that you didn't like something, and hopefully leave a comment about whatever complaint you have. Otherwise, I don't know how to, you know, I'm not omniscient. I won't know what it is you had a problem with. I do have a Patreon if you would like to support what I do here at Actually Hardcore Overclocking. If you would like to see some other AM4 motherboard, other motherboard breakdowns, there will be a playlist up on the main channel page. You can go check that out. There are AHOC shirts available. There's all kinds of, like, supporting me stuff is available down in the description below. If you don't understand anything about VRMs, there's links to that down in the description below as well from now on. So that's it for this video. Thank you for watching, and see you next time.